Hey you, it's me. Today we're going to cover fast and slow pointer pattern. Fast and slow pointers is a cool pattern that normally gets applied to linked data structures. Before we go any further, if you haven't already watched my video on linked data structures / intro to linked list, then I suggest you check that out here. Also, the link to that will be in the description of this video. In that video, I laid out the principles of how linked data structures operate. Okay, before we get into this pattern, let's build some intuition on fast and slow. Say we had two cars on a circular track, each in its own lane. They both start driving at the same time. Car 1 goes 20 miles per hour. Car 2 travels twice that speed at 40 miles per hour. It's safe to say that since Car 2 is traveling at twice the speed of Car 1, when Car 2 reaches the finish line, Car 1 will be at the halfway point. What did we learn from this problem? Well, we learned that we can actually measure a halfway point by using one car that drives twice as fast as another. More broadly speaking, we can measure a fraction of a distance, like 1/2 or 3/4, by adjusting our speeds of the fast car and the slow car, without ever even knowing the actual distance. Bear with me here, because this is not another Too Fast, Too Furious recap, I promise. But let's go back to our example. Car 2 just finished its first lap, and it's about to start its second. Will it ever meet up with Car 1 again? And if so, when? Well, we do know that Car 2 can finish one whole lap for every half lap that Car 1 is able to do. Well, by that logic, we can tell that Car 1 and Car 2 will meet again as Car 1 finishes its first lap and Car 2 completes its second lap. We can kind of generalize here and say that if we assume the fast car is always moving faster than the slow car, then eventually fast and slow will meet up again if they're going in a circle. To understand why this is valuable information, let's tweak our setup a little bit. Say we have two cars on a road that we do not know the shape of, but we would like to know if this track is circular. One way to prove that the road is circular is by showing the fast car and the slow car meeting again after the starting line. And on the other hand, if we know that our fast car reached the end of the road, then we know that our road is not circular. Okay, cool. I think we have some good intuition going on here. I do just want to mention one more thing. Cycle detection is a pretty common topic in graph theory, and very often a go-to interview question.
Graph theory?
Graph theory is a topic that studies what we refer to as linked data structures. In fact, it's a very wide topic, and computer science only employs a very small portion of it. But let's get back to the topic at hand. As you may have guessed already, the fast and slow pointer pattern initializes one fast-moving pointer and one slow-moving pointer. They both start at the same place, meaning they're pointing to the head of the linked list. But they each move or iterate over the list at different speeds. Finally, the information that we gain from these pointers can help us detect cycles or measure portions of the linked list, which, as you may recall, is an unknown value to us unless we iterate through the whole list and count. Okay, that all sounds pretty good. So now let's check out some LeetCode problems. Number 876 on LeetCode, middle of the linked list. Given the head of a singly linked list, return the middle node of the linked list. If there are two middle nodes, return the second middle node. And we can see here some pretty standard examples, but let's check out the constraints really quickly, because that'll give us some extra information. The number of nodes in this list is in range 1 to 100. That's really interesting. That actually tells us that at no point will they give us an empty list. Okay, this problem is pretty much the same as the first part of our car example, except instead of miles per hour, we measure speed as how many nodes a pointer moves per each iteration. And while our problem statement did specifically say that there will be at least one node in our list, it's a good habit to always check for a base case, where we check if head is none. This is the same base case that we use for all linked list methods. And we'll just return none if we don't have a head node, since the middle of an empty list would be nothing. Next, we want to define our fast and slow pointers, and then assign them the value of the head node. This way, both pointers start at the same starting point. Next, we create our while loop. Our while loop might sound like it could be a little tricky, but it's actually not. The fast pointer will always get to the end faster. So all we have to do is track if fast is not none and fast.next is not none.
Why is that?
Well, recall that our fast pointer is actually going to be moving 2 nodes at a time. So we're trying to access a potential node at fast.next.next. If we don't verify that fast.next exists, then we might end up getting a null pointer error when we try to access fast.next.next. Inside of the while loop, things are much simpler. We know for a fact that fast.next exists, so we can just go ahead and reassign the value of fast to be equal to fast.next.next, moving this pointer 2 nodes forward. And we'll end this while loop by reassigning slow to slow.next, moving it just 1 node at a time. And the reason why we don't have to check any node that slow iterates through is because slow is behind fast. So all those nodes are already verified when fast went through them. And finally, when we reach the end of our list, or in other words, fast is none or fast.next is none, we just return our slow node, as it's currently sitting in the middle of the linked list. So what would our time complexity be for this approach? It's easy to say the time complexity is O(n) because fast traveled the entire list and the list is length n. But that's actually not true. Fast and slow traveled the same number of nodes. They just had different step sizes. So our time complexity would be O 2/n. But remember, we drop coefficients, and the 1/2 is a coefficient. So we get O(n) for our time complexity. Okay, now that I think we have the hang of it, we're going to do one more problem. Number 141, linked list cycle. Given head, the head of a linked list, determine if the linked list has a cycle in it. There is a cycle in a linked list if there is some node in the list that can be reached again by continuously following the next pointer. Return true if there is a cycle in the linked list. Otherwise, return false. And you see here, they give us 3 examples. The first 2 actually do have a cycle. Our tail node is not pointing to none or null. It's actually pointing to another node in the list. And the third example, we see there's no cycle, just a lonely little node. In the constraints section, we can see that we would actually need a base case for this method, as they let us know that we might get a list with no nodes present. And the follow-up, challenging us to solve this using constant space, is right up our alley. This problem is just like the second part of our example. The nodes are like cars, where one is going to be slow and the other will be fast. And what we're trying to prove here is the list that we're iterating over is actually cyclical. What we said earlier was if fast and slow met again after the starting line, then we actually proved the road was circular. Convert that into programming terms. If fast pointer and slow pointer are pointing to the same node, then we prove that the list has a cycle in it. We're going to start like we always do with implementing our base case. If head is none, we're going to return false. Because if we don't have a head node, then we don't have any nodes in our list. So there's definitely no cycle. Cool. Now that we know we do have a head pointer, let's assign our fast and slow pointers the value of the head node. And we write our while loop just like we did in the other example. Because fast is going to move 2 nodes at a time, we need to make sure that fast is not none and fast.next is not none. The reason being to avoid null pointer access. Now that we're in our while loop, let's stop for a second and think about how we want to assess the value of our fast pointer and our slow pointer. Because remember, we want to check if they're visiting the same node. If we place our slow equals fast if conditional at the top of our while loop, we'll actually end up getting false positives every single time. Because remember, fast and slow start out equal. So for this reason, the first thing we want to do is move our pointers to their respective positions per iteration. And then after that, we can check if they're at the same node. Maybe you're wondering how exactly we're able to compare our fast node to our slow node, especially since node values don't have to be unique within a linked list. Well, we're not actually checking the nodes. We don't check if slow.value equals fast.value. We're comparing whether or not the memory addresses match. If they're equal, then it must be the same node. We'll return true if they are visiting the same node. And a little side note for those folks who are working in a pass-by-value language, like Go or C++. Your fast and slow pointers should be actual pointers or references. And our while loop will continue to repeat these steps until we've either exhausted the whole list or we did land on the same node. And for our very last step, we will return false outside of the while loop, because we know if we never return true within the while loop, then there was no cycle detected. What do you think the time complexity for this would be? In the event that we do not have a cycle in our linked list, our time complexity would follow the same reasoning as our previous problem. n/2 can be simplified to just O(n). Now, don't let the case where a loop is present intimidate you. For every node that our slow pointer traveled, our fast pointer moved a fixed number of nodes. We can call that extra movement C for constant. So between slow and fast, we have two complexities, O(n) and O(c)(n). And we always want to take the worst complexity to account for any extra time. This leaves us with O(c)(n). But we aren't done, because once again, we can drop the constant c as it's really just a coefficient. So our true time complexity is O(n). And those were just two ways that we can utilize the fast and slow pointer pattern. And really, when you think about it, it's just a slightly different twist on the two pointer pattern that we've now covered a couple times here. These problems were pretty approachable because for every one node that slow traveled, we just had fast traveled twice as much as that. So a 1:2 ratio for slow to fast is pretty easy to wrap your head around. I can definitely see how at first glance these types of problems might be intimidating, because cycle detection is definitely not something that you use in your everyday life. But the math behind it is pretty simple and easy to follow along, especially if you're able to visualize the problem, like I'm always saying. This should also be helping you get more comfortable with linked lists and how to traverse through them. I hope we didn't go too fast or too slow in this video for you. As always, thank you guys so much for watching. If there's any algorithm, pattern, or problem on LeetCode that you want to go over, let me know in the comments. And from me to you, have a great day. Number 876 on LeetCode. Graph theory is a mathematical topic that studies what we referred to as linked data structures. I need to not hit the mic. Wow. Cool. Wow. Cool. Boop, boop. Too fast, too furious. Too fast, too furious. Too fast, too furious. Too fast, too furious.
Too fast, too furious.